apparently there's a way to connect to the Hangout in the lobby or present from the lobby of the Hangout. So I'm going to try that, see if I can do that. Oh yeah, are you in a conference room? Present to meeting. More into our screen. I will share that. I am presenting to everyone. Look at that. There's also an interesting thing that I saw the other day is we did a hacking session on this on Friday. It's counterfactual fairness. So they are trying to compute using STAN, a probabilistic language. They're trying to compute fair, or whether or not your algorithm is fair or not, like in terms of the compass and all of those, or I guess what do you call it, like digital assistants or something. Yeah, and so their example here is from law school admission data in the US from the 90s, which, being from the 90s, we know it's definitely racist and sexist. And so they've shown how they are trying to look at how does it work? They take a set of sensitive variables and they're trying to generate a new variable, and then they're comparing each and every data set, each and every data point against the existing data points to see if they would be the same if those other variables changed compared to the rest of the data set. I haven't actually gone through the computation myself. We had the same problem that we had was like installing stuff and trying to understand the code. So we sat there for an hour and a half, and then we started training. And I think the training would have done and had taken another 10 hours or so. It was not very efficient. But it was very cool. I hope to look into that and get a bit more. So was it this one? No, that was definitely not it. Where did I have? I was looking at Meetup. Got all the links there. No, I have got the links in the. Should I have it here? Stanford projects. It's part of the docs. Surely it must be enough to do this. Anyway, I'll just go back to Meetup later on.
I think you said CS.
It's Rails something, isn't it?
Yes.
Yeah, that's right.
285.
That's right. That's true. There we go. Fantastic. And I'm pretty sure I've got the YouTube thing lined up anyway. So we were in model-based planning or reinforcement learning. We were in model-based reinforcement learning, I think, weren't we? That's the wrong one anyway. That's the PDF. Where was
The videos over the top.
Oh, that's right. Here's the streaming and recording. That's right. There we go. Haha, there we go. So where's the remote? This is running, so we should have. Yeah. All right. Great. This is useless. Great. Okay. So.
Need a cable.
Yeah. I've got an adapter for the HDMI, but if I remember correctly, the HDMI has been deactivated. So I have to unplug something. We keep telling people to please leave the HDMI activated, and they say, no, you don't need that because you can log in from the blah, 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 blah. And apparently it doesn't have full functionality. Despite YouTube being owned by Google and Hangout being a Google product, Google, if you're listening to me, which you supposedly are, then make your products compatible, will you? Yeah. Right. I will just go and get that adapter and grumble at the people who work with Google on the way in and out. Just. No, I'm not going to take the knife. The knife is actually, I brought oranges from home that I had to cut open. So if you want to, I wanted to eat them anyway, but if you want to, feel free to devour them. Car, so really yummy. Right.
Did you guys watch all the lectures before?
Sorry?
Did you watch all the previous
No, I
lectures?
think we started this one, which is a bit in the middle of everything. So, yeah. This isn't any reinforcement learning stuff. This is all control theory stuff. So, yeah, you almost don't need to worry about that.
Oh, okay. Is it what you're studying now?
Sort of, but not really.
Oh, okay.
Yeah, sort of come here to do some extra stuff.
Oh, okay.
Do you work alone?
I work here with Kasna.
Ah, okay.
I work with the Google products.
So it's your job.
But the hardware though.
Yeah.
I think you should work on it. Try.
So what do you guys do?
Mostly cloud deployments and cloud infrastructure. Yeah. I was just a developer, not into data science.
So maybe you can answer my question. So let's say we have a website, like some let's say online shopping. Oh, I think there was like one guy that had like some online shopping in Australia. I forgot how it's called that initially, but yeah, they've done some online shopping, and basically yeah, the site crashed. So yeah, so how quickly and how much you can scale such a website with like a cloud services? Is there like is there such a mechanism in place that you can, let's say you're expecting at 12 o'clock you expect like huge traffic, so you want to spin up some more services? How does it work?
Yes, sort of. Yeah, you're saying more traffic. I mean, it's also the application as well, right? If they had some like Grab application which cannot scale, doesn't matter where you put, either you're putting in cloud or or you run from your mobile device, it's the same thing.
Yeah.
It's also the application that needs to be scalable. Then
Okay.
that only cloud can actually enable to make it like scalable. What cloud gives us, it's most like some SaaS services.
Uh-huh.
Mostly like such as sales capability or those ones. Rather than building them from scratch, you find something natively.
Uh-huh.
Other than that, it's mostly still again the design and.
For those who don't want something sweet, here's something savory. Because I have to, responsible serving of alcohol, even though I'm the only one drinking alcohol, who cares? Right.
Round.
According to the people I know that work closely with Google, not for Google, running this on Chrome and not on Opera, which I just like, with the Hangouts extension, is supposed to be my best bet. So I'll give that a shot.
You weren't using enough Google products.
I wasn't using enough Google. Exactly. That's it. And it's already not working. No, of course not. So Hangouts extension. Great. It can read and change all your data on google.com sites. Oh god. Cool. Fantastic. Oi.
Such an ominous privacy setting.
Yes. No, don't get sad. Oh, it knows me. It totally knows me. Oh my god. Right. Cool. Cool. Okay. So, can I... I can probably, okay, I'll just, yeah. Okay. I'll just stop presenting. Stop this. Take this. Yeah. Mm-hmm. Your camera and microphone are blocked. Yes, they are. Damn right they are. Alright, that's what it is. Present to meeting. Aha! It does make some sound. Could you click on join, please? Thank you. Oh! It is only... Jesus. It makes me look like a total pig, but I'm absolutely sure that it's because the cans are so small. Like, they're really tight for the amount of beer that's in it. I didn't come in dancing or anything like that. I wasn't faking it. Anyway. And this has been happening with the last 2 or 3 cans by Dayton that I opened. So, not that this is a daily occurrence, maybe. Okay, share that to a screen. Presenting to everyone. Let's just do this. Can we do this? YouTube, yes. Let's have a look. Not looking good, is it?
Is your computer volume?
Is this a microphone?
As I've described it, yes, but you can actually get a closed loop policy out of it. Any
Okay,
other
so
questions?
that's not what we want. That is just dumb. Okay. Right. So if I did this and then my microphone would be, and then that would be this weird echoey nonsense is also, okay. Your algorithm is bad and you should feel bad. Okay. How do we do this?
Last time we just played on TV, right?
Yeah, that was when I connected to the HDMI, but we're not supposed to
Maybe you can
connect.
go to sound settings of the laptop. I know it's not Captain Obvious, but
Yeah, no, that's a
I
good
have like
point.
the same problem at home when I connect to TV, and it
Yeah.
just, you need to change it to TV.
Fair enough. Let's give this a shot. Did I leave? I think I left the meeting. I'll present to the entire screen, share. Let's give this a shot. Right. Let's see. It would be interesting if it showed up as a. Very interesting, because now I can't hear anything, even though my computer is all the way up.
The videos.
Oh, of course. Thank you.
Q's and V's? Well, they are actually Q functions and value functions. So the Q is
Right.
actually the total cost from now until the end if you take ut from state xt. It's literally a Q function. And the value function is literally a value function. Now, we're doing min instead of max,
Nope.
so the value is
I
now a
haven't
min
told
of
us
Q
because-
instead of a max of Q. But it has exactly the
Okay.
same meaning that it did before. So that's why I call them Q's and V's. What happens in stochastic dynamics? I'm going to go through this a little bit quickly because we're running out of time, but very simple answer. If your stochastic
Can you all hear
dynamics
this and
are
we should do this?
Gaussian,
Is that gonna
meaning
work?
that you have p of xt plus 1 given xt, ut is a normal distribution with a mean that is linear and some fixed covariance, then it turns out that the solution is exactly the same. So if you have Gaussian dynamics, turns out regardless of what your covariance is,
I remember that we said we
Entirely
would bring this back to a certain, like there was a starting part for this. We didn't just pop into this, right? So for you, nah, this.
The LQR stuff.
Yeah, because this is the dynamic programming for control, right? This is not.
Yeah, this is
Yeah,
control stuff.
yeah.
This is,
So, because I'm pretty sure. Wait a minute. I think that's what it was.
max
there was
of Q.
stochastic dynamics was
But
the next chapter
it has
and we
exactly the
want to-
same meaning that it did before, so that's why I call them Q's and V's. What happens in stochastic dynamics? I'm going to go through this a little bit quickly because we're running out of time, but very simple answer. If your stochastic dynamics are Gaussian, meaning that you have P of xt plus 1 given xt ut is a normal distribution with a mean that is linear and some fixed covariance, then it turns out that the solution is exactly the same. So if you have Gaussian dynamics, it turns out regardless of what your covariance is, so long as your covariance is constant, exactly the same method will give you the right answer. No change to the algorithm. You can ignore sigma due to symmetry. So you can check this as an exercise at home. As a hint for that exercise, the expectation of a quadratic under a Gaussian has an analytic solution. You can look it up in a textbook, and you can use that to figure out why this is optimal for Gaussian dynamics. The stochastic closed loop case. So there was a question before about whether this gives you an open loop solution or a closed loop solution. So you can actually show that if you...
Do you remember what the closed loop and open loop was?
Open loop is where you basically plan out all your actions all at once. And closed loop is where you take a step, get feedback from the environment, and then plan again.
Right, right.
You're
Yeah.
constantly replanning, whereas open loop is you just plan once and then follow that blindly. So when you have like stochastic case where something where you might not end up in the place you think, if you
Yeah.
open loop, you can just end up in really bad.
Yeah, so open loop would be a Roomba going, and you put your foot down and it just keeps banging against it.
Yeah, I think
Yeah.
the Roomba is actually a bit smarter. But
Yeah. Yeah.
But it's a the old like RC car. You don't
Yeah.
pull it back and it just goes straight forward.
Yeah.
Regardless of it doesn't do any kind of
Yeah.
update or anything. But
Yeah.
the Roomba is probably a closed loop. It's like constantly scanning and readjusting.
Yeah.
So.
use a time-varying linear controller, meaning that you actually choose your action according to capital K times x or s plus little k, that is also the optimal closed-loop solution for the Gaussian case. All right. Now, this was all for linear quadratic systems. We got on this track because we wanted to solve arbitrary nonlinear systems. So what do we do for nonlinear systems? We can extend LQR to this setting to get an algorithm called iterative LQR, or differential dynamic programming. The idea behind this method is actually very simple. It's an iterative method where at every iteration, we take our current sequence of actions and we estimate a local linear approximation of the dynamics and a local quadratic approximation of the cost using Taylor expansions. So we'll do a Taylor expansion of the cost, a Taylor expansion of the dynamics, plug them into the same LQR algorithm, and then repeat. So we needed linear dynamics and quadratic cost. Can we approximate it? Well, just use the derivative of your nonlinear dynamics to linearize them, and use the second derivative of your nonlinear cost to quadrasize the cost. So this is just the equation for a Taylor expansion.
Was this the algorithm that we'd already looked at, where you need derivatives all the way through your algorithm, and then there is the what is it called? The total deterministic policy gradient, or what it was called, DT, DP or something?
I think
DTPD?
that was
DTPG?
Yeah, DDPG.
DDPG,
is
yeah.
Not this.
Ah, okay. Now that's the one that's going beyond this and doesn't need the derivative. Is that the one? Is this the one before it?
I can't remember exactly.
Ah, okay.
I think it's it. But yeah,
Maybe
this
we'll
is just
get
a
there.
linear approximation.
Yeah.
So this is just the same
And then-
equation.
Yeah.
Well, for simplicity, I'm going to redefine, x minus x hat and u minus u hat. X hat and u hat are basically the previous trajectory that you had from your last iteration. I'm going to redefine them as delta q and delta u, which just declutters my notation. And then with this, I just run exactly the LQR method I had before. So I'll go through this pretty quickly. Here's a pseudocode for iterative LQR. Until convergence, linearize your dynamics, quadrasize your cost, run LQR, using delta x as your state and delta u as your action, then run the forward pass. Typically, you'd run the forward pass with real nonlinear dynamics, which is a slight modification, and then you update x hat and u hat based on the states and actions in the forward pass. Now, some of you might think at this point that this algorithm resembles another method that is very popular in in optimization, something that you've learned about before. Any hypotheses? Say that a little louder. Newton's method. It looks a lot like Newton's method, right? So here's Newton's method. Figure out the gradient, figure out the Hessian, set your x to be whatever minimizes this quadratic function given by the second order Taylor expansion, and repeat. So iterative LQR or DDP is essentially Newton's method for trajectory optimization. Locally approximate a complex nonlinear system via Taylor expansion, find the optimum, and repeat. So it's basically just Newton's method for trajectories. In fact, if you actually work through what Newton's method is, you'll get a very similar algorithm with a small difference, which is that Newton's method will have second derivatives of the dynamics, whereas iterative LQR only uses first derivatives. So there's a slight difference, but they both actually converge, and they both converge at the same rate. All right, so I'll skip over that. And what I want to do to conclude the lecture, well, first, some additional readings. If you want to learn more about this Newton's method for trajectories, this is the original work that proposed this idea called differential dynamic programming. This is a much more recent, modern kind of reinterpretation of the method with kind of more modern notation. So if you want to read some kind of tutorial style paper, I recommend Tassa et al. 2012. If you want to read the original monograph, check out the 1970 write-up. I'll skip over this. And the last thing I want to conclude on is just a video to illustrate maybe some of the merits of this type of approach. So I'm going to show a video from a paper by Yuval Tassa, Tomerez, and Emmanuel Todorov called Synthesis and Stabilization of Complex Behaviors. And this video illustrates, to me, very nicely kind of the power of model-based control. So this is actually using the Majoko simulator. They have a way to calculate derivatives through Majoko. And what they're going to be doing is they're going to be doing this iterative LQR, and they're going to be replanning every time step. So every time step, they calculate a new sequence of actions. And here's what they come up with. So in this video, they're going to show this iterative LQR procedure controlling different robots. So here it's trying to get this acrobat robot to swing up. Here it's trying to get this little hopper guy to stand up. And this is all done without any learning whatsoever, just using the model from the simulator and iterative LQR, essentially the method that I just discussed, where they replan their actions every time step. So here's the acrobat. Here it's just swinging freely without any control. Now they turn on control. The blue line shows where it's planning to go, and it swings itself upwards and stays balanced. Now, if they turn off the controller, it falls again. Turn on the controller, it swings up. Nothing was learned. Everything here is invented essentially on the fly by the optimizer. So trajectory optimization really does work very well if you have good models. Now here they're going to apply some random wind to it to perturb it, and it sort of stays upright in the wind. So there you have it, it's staying upright. Here they're going to have a little simulated swimmer. The simulated swimmer needs to move its body and use the viscosity in the fluid to swim, and it's trying to reach the green circle. So this kind of undulating swimming gait just emerges as a consequence of the trajectory optimization. There it goes. And then it's trying to avoid the red circle, so they're going to kind of harass it a little bit with that red circle to get it out of the way. And it swims for fairly long distances. Now keep in mind, there is no neural network policy underneath this. It's all just planned and replanned every time step. Here they're going to try to torture this little hopping robot. So here it's just passive. Now they're going to apply some forces to it using a little user interface. And then eventually they'll turn on the controller and try to get it to stand up and deal with these perturbations. So now turn on the controller, it automatically figures out how to stand up, and then they're going to push it a little bit. So if we could actually get dynamics models that were good enough, then this stuff could in principle all work. Here they're going to get it to do a little flip, and so forth. Can move this forward a little bit. There's a little humanoid later on. So here this humanoid is going to figure out how to stand up. It's going to figure out how to respond to perturbations. And again, everything is being recomputed every time step using LQR. All right, so don't try this at home. All right. Well, so hopefully this illustrates a little bit the kind of stuff that we can do with optimal control if only we had good models. So next week we'll learn about how we can get good models and do deep RL with this. All right, this is good. Okay, so for those of you watching it online, I have to talk into this blue thing, otherwise none of you will hear me, but that's okay. So today we'll be talking about model-based reinforcement learning. A few quick notes. Homework 3 is out. We'll check the due date. I think it's due next week, but someone just told me that we'll post it on Gradescope that it's the week after. We'll confirm that and we'll post it on Piazza. But either way, make sure that you start earlier on this. It takes a little while to run the Atari part of the Homework 3 especially. Today's lecture. Today we're going to cover the basics of model-based reinforcement learning. One can crudely characterize the basics of model-based reinforcement learning as simply being learn a model and then use that model for control. But this very straightforward kind of naive approach often doesn't work very well. So we'll find out a little bit why, and we'll discuss how we can make it work better. We'll then talk about the effect of distributional shift in model-based RL and how we can mitigate that. And we'll talk about uncertainty in model-based RL and how in model-based RL especially it's very important to learn models that are aware of what they don't know. Then we'll, in the second half of today's lecture after the break, we'll talk about model-based RL with complex observation spaces, like images. And then next time, on Wednesday, we'll talk about how we can do model-based RL with policy learning. So today, all of the methods that I'll discuss are kind of in that open loop planning regime, and then on Wednesday, we'll come back to policy learning. So the goals for today's lecture will be to understand how to build model-based RL algorithms, understand the important considerations for model-based RL, how to design good model classes, how to estimate uncertainty, and so on, and understand the trade-offs between different model class choices. All right, so why should we think about learning a model? Well, if we knew this f of st comma at, we could use the tools from last week to actually plan through that model and make decisions. And we saw at the end of last week's lecture that if you actually have a ground truth model, you can do some pretty impressive stuff. So if we could only acquire a model that is sort of comparably good to the true model, then we could get some really interesting behaviors to emerge. And of course, this is sort of in the deterministic case. In the stochastic case, you could imagine that you estimate the probability of the next state given the current state in action. So let's try to think about learning f of st at from data, and then use that learned model to plan through it to actually take useful actions in the world. So from this, we can kind of write out the model-based reinforcement learning algorithm version 0.5, and I call it 0.5 because it's sort of questionable as to how well this would actually work in practice, but this is our first kind of baby version of a reinforcement model-based RL algorithm. Step 1, you run some kind of base policy, we'll call it pi0, to collect a data set, and it's a data set of transitions. It's a data set of tuples, S, A, S prime. Then we're going to use these tuples to learn a dynamics model, and you could learn a deterministic model or a stochastic model. So here I have it written out in a form that maybe makes sense for a continuous state deterministic model, so you minimize maybe the squared error between the model predictions and the true next state. If you have a discrete state, maybe you use something like a cross entropy loss. You could also have some stochastic model with some arbitrary parameterized distribution, and that would change the form of that loss function. So that loss function at the end, in general, this thing would be some kind of maximum likelihood thing. So once you've learned the model, step 3 is plan through this model to choose your actions. And if you've got a good model, then step 3 should work well, maybe even as good as the thing that we saw last week. So does this actually work? Well, yes, in some cases it actually works decently well. This is essentially how system identification works in classical robotics. So if you have a kind of a background in engineering or robotics and you've heard the term system identification basically follows.
What is it?
So if you have, so say you have like some robot arm and you don't, but you don't know exactly sort of how heavy it is or something, like how much mass it has.
Mm-hmm.
If you run a command, like say you want it to turn this far, or whatever, you apply a torque,
Mm-hmm.
you can basically just work backwards. So if you apply this torque, and you get to this point, well, the thing must be this mass.
Okay.
It's basically that concept.
Mm.
But you can do it for more complicated systems.
Yeah.
So yeah, you're identifying parts of the system.
And that, of course, only works because you know how much torque you apply.
Yeah, you need to know something.
Yeah.
And so it's almost, you're working backwards.
So with a human, if you wanted to model a human, say, could you do a similar thing? Like if you know how heavy a person is, for example, and you and you see them jump, let's say 10 times, and they get to an average height.
Yeah.
Would that allow you to apply mechanics to the joints and muscles and say?
Yes, theoretically.
Okay.
Like so if you knew how much they like weighed in total,
Mhm.
and then you saw like how high they jumped,
Mhm.
you could just use the physics basically
Yeah.
to just see how much torque they applied, and then you could roughly model out all the joints in the human,
Mhm.
and then so in order to generate this much force, you would need to apply this much torque there, and this torque there, and this torque
Mhm,
there.
mhm.
But probably doing that in practice. Actually, maybe not. I don't know. But yeah, that's theoretically what you do.
Mhm.
And so you could say, to jump this high, the overall torque needs to be this much.
Yeah.
And then if you're like this, if your model is like this,
Mhm.
you need to apply this torque there, this torque there,
Yeah.
this torque there.
I'm thinking of, for example, the robot that Ripley was controlling at the end of Alien.
Yeah.
That thing. So I would imagine you wouldn't necessarily jump around with that. You would probably system identify each component individually, and then you'd know.
Well, with something like that, you make
just
it
weigh
so
it.
you know.
Yeah. Okay. Fair enough.
But
Yeah.
I was thinking because my research was actually put my little fingers a few years ago having an operation, and then after recovered, I had to go through the physio,
Mm-hmm.
and my grabbing force
Yeah.
without little finger was much less than just adding a little finger.
Mhm.
So actually coming into can you like adding in a model like for example, if I use 2 fingers, how much force can I do? Can there something apply to the scenario, or is just not relevant?
Yeah, it's kind of the same thing. You're basically using a model to apply something known.
It's
and
actually
then measure.
quite less kilogram I can grab.
Mm-hmm.
Yeah, just a little finger.
Yeah.
Yeah, so for now I'm really careful with my little finger. But it's just something when you talk about it, like this is something like you can predict the bones, like you know what I mean? I'm probably not explaining
it might
very-
no. I know what you mean, but it might be it's like there could be like lots of reasons why you might like lose strength or something like that.
Yeah.
But you can certainly use it to figure out something's wrong. But then it's kind of just measurement.
I think again on Netflix. Looks like I'm watching that. That's not true. I know. So there was this guy that was climbing, and actually he was using saw, like a table saw, and he was like not using it properly, and I think he lost the thumb.
Yeah.
I think, or like one of the fingers. Anyway, he was like a very good climber, and he still like accomplished some enormous thing without one of the fingers.
Yeah, I think so. Because like, I don't use this hand to carry my grocery bag.
Yeah.
Because my right hand can carry a heavy one. Then when I put the same bag onto it,
Yeah.
the physio used like a grip to measure
Mhm.
the strength.
Yeah.
But when I tried out on myself when I went to the supermarket, by that time I can only carry 1 or 2 stuff in this hand, in my hand. But this one can be like a few
Yeah,
more.
but I think you can like actually exercise that.
Yeah. But
Yeah.
yeah.
Because I had like a colleague that was trying to do some kind of bodybuilding, and he was saying like it took him like 2 months or something for the both hands to be
Yeah,
similar.
3 months.
Similar strength. So,
Bookclub is 3 months. So we can.
so going back to this, that can be summarized as somehow empirically
Yeah.
measuring the properties of the system.
Yeah. So
Mhm.
in like the crudest way, I just looked it up just to check. Like that's what you're doing. It's like the most crude form of learning. You're applying some input, measuring the output, and
Yeah.
then using your sort of knowledge of physics to be like, oh, that's the relationship
Yeah.
between the system. So if I was to push this across there, I could figure out what the friction is or whatever it is.
Yeah.
So
This is
It's
even
a-
more messy than a
it's-
beer.
it's kind of like a very crude.
And what would be like a practical application of that? I think that's a silly question.
In physics, you have the application of getting a effective electron weight. So I would imagine it's a similar thing where you measure. Hey,
Also, very, I think,
already.
sarcastic, sorry. Very
Yeah. So in physics, you have a case where you get an effective electron weight. So instead of having the electron mass as we know it, from being like pure and, if you will, sort of in wild, in a material, when you have all sorts of interactions that you can't really quantify, you just measure the effective electron mass. Like you have got the equations, and what you change is like, okay, I know this equation which contains the electron mass as part of its acceleration, blah, 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 blah. And so you measure your effective output and your effective sort of throughput and so on, and you just derive an effective electron mass for that, and you can just use the same equation as if the electron was heavier, because it just takes so much more force to pull it through and so on. Yeah. And instead of saying this material has a density, blah, blah, whatever, you don't say any of that. You just change this other number to make it work.
Exactly sort of the same thing.
Yeah.
You might have like a really complicated system
Mhm.
and stuff, but you can
Yeah.
just treat it like a black box that you
Yeah.
apply this torque, you
Mhm.
get this much
Yeah.
output, rather than having to sort of deal with the complexity.
Yeah. Mm-hmm. Yeah. Very interesting. Hey.
Hey, sorry to interrupt. Like this is more about the physics aspect of usage of what do you call this?
Reinforcement learning?
Yeah.
Oh no, this was we got a bit sidetracked because we were looking at he was referencing a. I'll go back
Because
just
when
one
it said
slide.
electron has a mass, I was trying to understand. Okay, does it have a mass?
Yeah. So the equivalence that we were drawing was he made a reference to a practice used in robotics. And there is a similarity in physics to what they're doing in robotics, where, just like Patrick said, you eventually make one measurement to make your life easier, to get a number that you need without measuring every single bit of your system. You measure a number that gives you the most information, most approximate and useful information about this black box system, so that you can work with it. Does that summarize it well enough? Yeah, cool.
Be even as good as the thing that we saw last week.
Yeah.
So does this actually work? Well, yes. In some cases it actually works decently well. This is essentially how system identification works in classical robotics. So if you have a kind of a background in engineering or robotics and you've heard the term system identification basically follows this recipe. You run some base policy, you collect some data, you fit the parameters of your model, and then you use that model. Now, some care needs to be taken to design a good base policy. So if your base policy just sort of sits there and does nothing, then you probably won't actually collect data that is useful for identifying a good model. And this kind of thing is particularly effective if you can hand engineer your dynamics representation, your model class F, using your knowledge about how the system really works. So this kind of stuff can work well if, for example, you know that you're controlling a robotic arm with 7 links and revolute joints, and all you need to know is how heavy each link is. So if you have a small set of physical parameters, this kind of 0.5 version of the method is a decent way to get an estimate for the value.
I'm just stopping it here so that you can catch up on what was discussed before. Does this make sense? Like, he is looking at a deterministic model where there is a definite outcome, like your state S prime, and you're basically learning what happens at each state Si if you take action AI, and then you get to, and the model, of course, if the model predicted each state S I prime correctly, yeah, then the error would be 0, and we'd have a perfect model.
Okay.
Yeah?
Value of those parameters. But if you're training a very complex dynamics model, like a deep neural net, this tends to work somewhat poorly. And that's what we're going to try to understand on the next slide. So this is here we're going to sort of confront one of the most basic issues with model-based reinforcement learning. Let's say that my task is to get my agent to climb to the peak of this mountain. And step 1 in my model-based RL version 0.5 algorithm is to run my base policy, which could be some kind of random policy, to collect some data that I can use to train my model. So maybe this is what my base policy does. It goes for a little random walk on the slope of this mountain. Now, if I use that data to fit my model F, my model will probably tell me something like, the further to the right you go, the higher you are, right? So the peak is somewhere to the right. So if you go to the right, you'll get higher up on the mountain. So just go right, right? That's kind of a reasonable thing to conclude from the data collected along those red paths. So then if I take that model to be essentially the truth, and then use it to plan a path that maximizes my reward, that's step 3, I'll probably end up doing something like this. So what really happened here? I mean, maybe the obvious answer is that, well, my model wasn't really a good model. I thought it was better than it really was, and as a result, it led me astray. But more mathematically, this is actually an issue that we've seen before. The issue is that we have some kind of function approximator, in this case f. It was trained on a particular data distribution, and then we used it to extrapolate beyond that data distribution in ways that were kind of unjustified. So the training data, the training states, came from the distribution p pi 0 of s. When we then go to actually control our system to reach the desired goal, we're going to go to different states. Let's say that pi f is the policy induced by planning through f. Then the states that we visit come from some other distribution p pi f of s. And that other distribution is very, very different from the one that collected the data. So that means that our policy, the implicit policy, the one induced by planning through f, ends up trying to act in states that are very, very different from the ones in which the function approximator f was trained, and therefore f isn't really making reasonable estimates from those states. So we've seen this problem before. We saw it when we talked about imitation learning. And we even saw something like a solution to this problem. So does anybody have any suggestions about how we can address this issue for model-based reinforcement learning?
Any ideas?
So somehow land the value along the way?
You mean like in just like we did before, where just don't sample and plan, just plan at each step.
Yeah.
Compare to what you know and how different it is.
Yeah. I don't know. It's just like kind of the first something that comes to mind.
The problem is that when you're acting, well, when you are training your dynamic model, you collect a certain set of experience, a certain number of states. But when you actually act, you're in a different state, a different set of states, and so you've never actually seen those. So you can either just keep continuously learning dynamics,
or maybe
force your model to only go places that's seen before, which is kind of
not get very far.
Or maybe define the success and just flag if the episode ended with success or not.
Something TD learning comes to mind, right? Where you keep learning.
Yeah.
I guess. Because this is an off-policy thing, right? It samples for a bit, then trains, and then just goes off and does stuff.
Yeah, well, you're actually learning the dynamics of the world rather than learning the policy.
That's true. Yeah, that's true.
So like, it's almost like you have a map of the world
Mm.
that only exists, that only covers a certain
Yeah.
part of the.
Yeah. So in this case, what would this is not even your experience replay buffer or anything. This is Well-
This is so in the, I guess the RL lingo, it's P of SA. So
Yeah.
you're learning about if I'm in some state
Mm.
and I take some action, where
Yeah.
do I end up? As opposed to what should I do in that
Yeah.
state.
Yeah. So that's more like learning the critic that learns the value function. Is that similar to that?
It doesn't really tell you about anything about like how good
True,
it is.
that's
it just
right.
tells you
Yeah.
that if you're in this
Yeah,
state
that's true.
and you do this thing, you'll end up in this other state.
Mhm. Yeah.
So it doesn't sort of make any value judgments.
Yeah. Yeah.
we Captain Obvious today, but yeah, is it like a definition of the model?
Yeah.
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 It's
Yeah.
like it literally just it is a map, but without marking where the treasure is.
Right.
kind of thing.
So, okay. But we're getting a new policy out of it, right? So we're getting a model for F, which is the dynamics of the environment.
Yeah.
And then we're trying to use that model to then form a new policy because there is pi F.
Yeah, but the step 3 is planning. It's not actually a policy. So you have some sort of cost function, and then you're like running through
Yeah.
the dynamics to see like if I take this action, where do I end up? If I
Mhm,
take that
mhm,
action,
mhm.
and then sort of
Yeah.
comparing the costs of all those states. It's dynamic programming.
Right. Yeah, okay. Mhm.
So yeah, what you're actually learning is the model of the world. And
Yeah.
You're just doing
Mhm.
dynamic programming kind
Yeah.
of thing.
Mhm.
Sorry to jump in. I'm still trying to understand. At each and every state, it is going to reevaluate its the way, like what action should be taken, or it's more like.
That's what we were just discussing. It's not.
It's not?
So the thing is that what F of S and A is it just observes what it's doing and where it's going, and then it tries to create this model F such that F is the most accurate or as accurate as possible for what happens if you take a certain action in a certain state.
Yeah, that's what
But
I'm
it says
saying.
nothing about whether that's good or bad. It says nothing about whether it should do that or not. It's just trying to assess whether that is really what happens or not. And then from there, the next model, as it goes, tries to get an idea of what the world is like and what it then should do. But all of this is based on this initial. Based on this initial. Someone else got stuck by.
Yeah, I was running.
Yeah.
I have meetings and I felt it's very
Yeah.
nearby. I was walking anyway. Because I was of the view that it takes action at each and every state. When you find a new state, it takes an action. But like you're saying, because when you say pi of.
Maybe it'll get to that because I don't know how it would.
So this is not. I don't know. Is RL, but so it's not a policy. It's a planner. So every
Yeah.
single state, it says I'm here. If I take this, and this
Yeah.
step, what will I get? And then it does the next step, and then it replans each step,
Yeah.
as opposed to a policy, which is almost just like a lookup table. If I'm in this state, I do this.
Yeah.
If I do
Yeah,
in that
yeah.
state, yeah.
Yeah.
So this is kind of in step 3. There's a big cost function. That's
Yeah.
for this is like how high you are.
Yeah.
Does it mean that it like the item like point to a dynamic model? That means that the step that you take, you trigger it like you calculate the course and give them a model or plan.
So the third step, recalculates the plan,
Yeah.
but it doesn't update the model of the world.
Okay.
You can only do that by actually like getting actual experience in the world.
Mm.
Yeah, I think you're right. Sorry, I think you're right. If you add a cost function, you know, or even if you take entropy or the cost function, you can find how far it is. Is it like what you're trying to do?
Yeah.
Can you minimize the entropy? I think.
So one of the things that they're not saying, but that I assume must be given somehow, because otherwise you wouldn't use f, right? So there must be a generalized definition of the state, so that you can so that you can recognize the state when you walk out of the part of the world.
Yeah.
So it wouldn't necessarily be like, it could be a dumb state, like there's 3 pebbles on the ground. That could be a state, right?
Yeah.
And then I go up or
for,
something.
For example,
Yeah.
something like it might be XYZ coordinates.
Yeah.
And then your cost function might be negative z.
Mm.
So if you're in
Yeah.
states, the z is usually the vertical direction.
Yeah.
So if you're in states with high z,
Mhm.
they're low cost. So your model should want to
Yeah.
plan uphill.
Yeah. Mhm.
Um, But your
Yeah.
dynamics model just tells you if you're in this
Mhm.
state, the next state is up or below.
Yeah. Mhm. Yeah. So that, in this case, the model doesn't think that the mountain's going to end.
Yeah,
That's
so
what it.
the model, like when you're right on that edge,
Yeah.
the model's like, yep, if you keep going this way,
Mhm.
it'll be higher. But
Yeah.
because you've never experienced that, you don't
Yeah.
know any different.
Mhm. Yeah.
Yeah, I was just trying to compare it to the optimization model. I know they're not relevant, but I'm trying to compare the optimization model.
Mhm.
I'm trying to measure at each and every point when it's trying to find the best optimal point.
Mhm.
Yeah.
Yeah.
Cost function, the function.
Yeah.
It says, okay, I'm basically not as optimal, then you have to do
Mhm.
reiteration
Yeah.
and all the process.
Mm.
Okay, thanks.
It's
back
very,
there.
very sort of simple.
Right, so you could do something, the answer was you could do something like Dagger and you could go back and collect some more data. So let's try to imagine an algorithm that actually does that. So this is a distribution mismatch problem, and it becomes actually exacerbated as we use more expressive model classes because they can fit the training distribution better and extrapolate worse. So can we make p pi 0 of s be equal to p pi f of s? So let's borrow the lesson we learned from Dagger. So we're going to run our base policy pi 0 to collect our initial data set. We'll use that initial data set to learn a dynamics model f. Then we'll plan through f to choose actions. And then we'll execute those actions and add the resulting data back to our data set. So we'll actually, just like in Dagger, we aggregate the data. Here we also aggregate the data. Now in Dagger, remember, we needed to get our data labeled with the ground truth function. For imitation learning, the ground truth function was the true policy. Here we're not learning the policy, we're learning the model. So the true function is the true model. When we execute those actions in step 4, and we add additional data from the real world to our data set, we are in effect labeling the SA tuples with the true S prime. So this is essentially implementing Dagger, but for models rather than policies. And then of course we repeat this process, and if we repeat it often enough, eventually the model F stops changing, and at that point we're actually collecting data from P pi F. So that will address this distributional shift problem. So where have we seen that before? Well, we saw it before in imitation learning. So I call this model-based reinforcement learning version 1.0 because this is kind of the first class of model-based reinforcement learning algorithms that actually kind of has a chance of working in the deep RL regime with high-capacity function approximators. Now there's a little bit of a detail and a little modification of this method that can actually make it work quite a bit better. The current method, as I described here, should in principle work and converge decently well, but it might take quite a while to get there because you need a pretty good model if you want to plan through it and then execute a big long trajectory. So you can do a little bit better. Let's imagine that you're not doing this hill climbing thing, but instead you're driving a car. And you make a little small mistake. So maybe your model is a little bit incorrect and your model says, the car will go straight if you turn the steering wheel a little tiny bit to the left. It's a small innocuous mistake, so you'll turn the steering wheel a little bit to the left because you want the car to go straight, but now the car is not going straight anymore. And now you're in a slightly different state, and you'll probably turn the steering wheel a little bit more to the left to compensate, but that's of course the wrong thing to do. And eventually you'll get off the road. Now, if you run that model-based RL version 1.0 algorithm, you will actually try doing this, append the resulting data, and hopefully get a better model. But you'll never get a model that's truly perfect. It might take you a very long time to get a model that is good enough such that these mistakes don't really compound. So you can actually address this issue decently well, even if your model is highly imperfect. Does anybody have any ideas about how to do that? let's say that our model is imperfect, but generally has a reasonable idea. So it says, you'll go straight if you turn the steering wheel a little bit to the left.
Do you look ahead?
Do you look ahead? What does that
More
mean?
data.
Look a certain number of steps
Instead
ahead.
the little samples at
And
higher
then
rate.
pick the action for the trajectory that maximizes your work.
Okay, so you could, for example, plan for the future, pick one action from that plan, execute that one action, and maybe you could try planning again. So a reasonable strategy to take here is, instead of just generating your plan to steer the car to drive along the road and then going and blindly executing that plan, what if you keep an eye out for what's actually happening, and if what's happening deviates from what you had expected, just try to replan again and see if you can correct that mistake. So maybe if you did what your model told you and steered the car a little to the left, now you're not going straight anymore. Well, once your mistake becomes big enough, if your model is kind of decent, it should eventually tell you that you should correct by steering back to the right. If you had just blindly followed your plan, then you wouldn't have realized this, but if you replan from the state that you actually reached, rather than assuming that your model would be correct, then you might still have a chance to fix this. So this gets us model-based reinforcement learning version 1.5. You run some base policy, just like before. You learn your dynamics model. Then you plan through your dynamics model to choose a sequence of actions. But then you only execute the first planned action and observe what actually happened after you took that action. You append the transition SAS prime back to your data set, so you collect the data, and then you plan again. So you're essentially replanning every single time step. So that means that if the car deviated from the trajectory you thought it would follow, you would replan and try to correct. And if your model is not perfect but kind of okay, this can actually make the performance of this method a lot better. This is referred to as model predictive control, or MPC. So if you see someone say, oh, I'm doing model-based RL with MPC, what they mean is that they're replanning every time step. And then of course you have this outer loop where every, let's say, n steps, you go and retrain the model on all of your aggregated data so far. This is basically meant to help with model errors. This doesn't really change the high-level idea behind the algorithm. It just makes it so that you get better performance sooner before your model gets completely perfect. And in fact, in very complex environments, your model might never become perfect. Maybe your model is not big enough, or maybe it needs too much data. So this can actually give you pretty good performance even with highly imperfect models. And you'll actually be implementing this for homework 4. So this model-based RL version 1.5 algorithm is a pretty decent algorithm. You can actually solve a lot of really interesting problems with it, and that's what we'll be doing in our model-based RL homework, which is the next one after this.
This is exactly what you do in control, except instead of learning the dynamics model, you know it just from physics.
Yeah.
And it's the same kind of idea that you can get away with a simplified dynamics model because you're planning every kind of step.
Oh, like when your tires slip and that sort of thing.
Yeah. So you don't have to take into account all the crazy complexity. You
Mhm.
can just sort of use a simpler model,
Yeah.
which is easy to compute. Except in this, you're learning the model instead.
So last week on Wednesday, I actually showed you this video where the true model was used to control a bunch of little simulated robots. Actually, in that video, let me just go back to the video for a second. In that video, they also have a section where they intentionally gave it the wrong model. So here, they told the planner that the little hopping robot is half the weight that it really is. And here they told that it was double the way that it really is. And it's not perfect, but because it's replanning every single time step, it actually does something kind of decent. So if you were to just plan in open loop and then try to execute that plan, you wouldn't get anything reasonable. But if you replan, then you can actually do decently well. And in fact, replanning compensates for imperfections in the model and imperfections in the planner so well that you don't even need to plan particularly effectively. So you could, for example, use much shorter horizons. You could use a weaker planner, like a random shooting method, instead of the kind of gradient-based thing that they're using in this video. And even just kind of, the simple random sampling methods can actually work pretty well if you replan every single time step. So to a large degree, this replanning stuff can compensate for model errors weaknesses in the planner, and so on. Okay, so that's what was used in that video that you saw at the end of lecture last week. All right. At this point, since I've basically presented the first algorithm that you can set up that will actually work well, do any of you have any questions about this approach? And this is a good time to ask those questions because you'll all need to implement this for homework 4. Yes, back there. Yeah, the question is, this sounds kind of expensive. Doesn't this take a really long time? It does. So, in fact, in homework 4, you'll find out just how expensive it is. And that's actually part of the reason why we might actually prefer planning algorithms for step 3 that are not as good in terms of producing excellent plans, but are more efficient or easier to parallelize. So for example, the random shooting method that I presented last week is really a terrible optimization method. But if you have a GPU and can run a bunch of rollouts in parallel, it can be a lot faster in terms of total time needed to compute a plan than, for example, the fancy gradient-based optimizer that is used to make this video. Yes, here?
Don't you introduce correlation between the observations when you're trying to do these squares? Because they're not IID, right? The samples.
Right, so the question was about step 2 in this algorithm. Aren't you introducing some correlations when you're collecting data and then running step 2? So to be perfectly clear, in step 2, we minimize the error or maximize the likelihood on all of the data seen so far. So in a practical implementation, step 5 would append your data to a big buffer, and then step 2 would do like an entire run of mini-batch SGD on the whole buffer. So if your buffer is big enough, every step of that mini-batch SGD would be decorrelated. So you're not actually updating your model online with every single transition you see, you're just adding the transitions to the buffer, just like in the deep Q-learning discussion we had before, and then when you actually run training, you sample IID from that buffer. Back there?
What do you mean by even random sampling and nothing above?
So this is the most basic algorithm that we discussed last week, which is sample random sequences of actions and take the best one. It's not a bad optimization algorithm. Actually, it's a very bad optimization algorithm, but it's very fast. Any other questions? Yes? Can you use cross-entropy method also? Yes, you can use cross-entropy method. You can use CMAES. You can use pretty much anything. The question is how would you want to strike that trade-off between computation cost versus getting this thing to actually run at something resembling real time. All right, so we discussed a method for doing model-based RL. Let's talk about how well it works. So this is a plot from a paper by Anusha Nakabandi, who conveniently enough is one of the TAs this semester. So if you have any issues with this plot, you can go to her office hours and ask her. But what this plot is showing is what happens when you run model-based RL, and what happens if you then run model-free RL, starting from where model-based RL left off. So this is the cheetah task that some of you might remember from homework 1. This little brown part of the curve shows what happens if you run pure model-based RL, basically the method that I described on the previous slide, for about the equivalent of 10 minutes of real time. So this is if the cheetah was actually running for 10 minutes. And it goes from a reward of like close to 0 to about 500. And it pretty much kind of plateaus there. If you then run model-free RL for about 10 days, it does a lot better. It gets to a reward of above 5,000. So this is what a reward of 500 looks like. It's not terrible, like it's kind of shuffling forward a bit. And here's what 5,000 looks like. It's kind of a nice, healthy cheetah run. Okay, so what's going on here? Why is it that the model-based RL algorithm kind of improves a bit, but then seems to sort of get stuck? Any hypotheses? Does anyone have any guesses? Why doesn't this model-based RL method end up doing better?
Is that similar to what we discussed before, where it's kind of stuck in this loop where it doesn't explore? Yeah? Whereas with model-free you have to explore, I suppose, in order to learn your Q function?
Yeah. I'm guessing that's how it would be. Yeah.
I don't know, maybe this planning and short horizon actually happens
But it seems that
the goal, visibility of the end goal. I don't know.
but it seems that if you just run it model free, it doesn't get as high as doing the combo. So maybe it's a good like starting point. But then it doesn't explore.
Yeah. That's what I was supposed to say.
Yes.
Because they kind of got stuck in a local maximum probably.
Okay, so perhaps something got stuck in a local maximum, like maybe the model hit a local maximum of its likelihood. That could be. Yeah.
Maybe like never got to see the states that give high reward, just like I guess it's the same idea.
Yeah, maybe somehow it didn't get to see like the important states, the good states. That could be. Back there?
Whatever you use where the model is not expressive enough.
Yeah, maybe Anusha didn't set up quite the right model class. That's quite the accusation. You could ask her about that analysis. I think she set up a pretty good model class, actually. But here's maybe the problem. Maybe the problem is that Anusha had to solve an impossible problem here. See, when you're over here, you have very little data. Those 10 minutes of cheetah running, yeah, it's great that you can learn in 10 minutes, but that's not very much data. So you need to use a function class that doesn't overfit when you have a very small amount of data in the beginning. But you need a function class that's also expressive enough so that it still has enough capacity to capture the true model when you're closer to this regime. It turns out to be pretty hard to do that with neural nets. It's especially hard because of how model-based RL works, because the planner in model-based RL is explicitly trying to find plans for which the model predicts a high reward. So if the model makes mistakes and erroneously predicts high reward, those are exactly the paths that the planner will select. So here's our model-based RL version 1.5 algorithm. And let's imagine that our model is quite expressive. So this is a very expressive model. In this case, this is a high-degree polynomial fitting a bunch of points. The actual points are distributed according to a linear function plus some Gaussian noise. So the black line shows the true function. But the model fit these points very, very well. And imagine for a second that what I'm plotting here is not the actual predictions from the model for the next state, but actually the predictions for the model as a function of a sequence of actions for the total reward. So the y-axis is reward. Well, it's very tempting for the planner to then select the input that will cause it to go to that peak predicted by the model, even though that peak is not real. Essentially, any mistake the model makes where it grossly overestimates the reward that it will get for some sequence of actions is a mistake that the planner could then exploit, select those actions, and produce pretty nonsensical behavior. In fact, there's a much better thing that the planner could do if it had the true model. Essentially, since the true function here just happens to be linear, the further to the right it goes, the better it will do, but that peak is all the way on the left. The peak is there because the model, in this case, is overfitted, but any model makes mistakes of some sort, and the positive mistakes will get exploited. So this is a big problem, and this problem becomes especially exacerbated in higher dimensions. So this is a one-dimensional example, and you can kind of intuitively imagine that you have this this manifold of reasonable behavior, and somewhere in that manifold there are little holes that produce mistakes, like this one, right? So this, you can kind of think of it as a hole. The higher dimensional this object is, the more opportunities there are for this function to have these holes in it where it goes outside of the region where it was trained. So in higher dimensional spaces, these kinds of screw-ups become the norm rather than the exception. And there are so many of these mistakes that even if you run additional on-policy collection, even if you keep appending more data, you might take an extremely long time to find all the mistakes, collect data for those mistakes, and fix them. And that's kind of one of the dominant hypotheses about why that learning curve on the previous slide actually saturates at 500, because there's simply too many mistakes that the model is making for this on-policy collection to catch them all and to fix them all. So perhaps what we could do is we could try to estimate whether our model is right or wrong. So these kind of mistakes, they happen in places where the model is incorrect. And the model is not just going to be wrong arbitrarily, it's going to be wrong in places where we didn't see enough data. So perhaps we can use uncertainty estimation to help detect where the model might be wrong, and patch up these holes that way instead of having to collect data for every single mistake the model might make. This is an example of a function approximator. This is not a neural net. This is actually something called a Gaussian process that is providing an estimate of its uncertainty. You can do this with neural networks as well, and we'll actually discuss that shortly. But this is a Gaussian process. It's a particularly convenient but not very scalable function approximator that estimates its uncertainty. So the true function here is shown by the dotted red line. The thick red circles are the observations. And then the shaded blue region is a 95% confidence interval. So this Gaussian process is telling you that maybe close to the red dots over here, it really knows what's going on, and far from them over here, it has a very wide region of uncertainty. So it's saying, well, most likely you'll be here at the mean, but I really don't know, so you could be anywhere in that blue region. Now that is a model that is aware of its uncertainty. So imagine that we were using a model like that to solve a little navigation problem. So we're taking a walk on the shore of the ocean, and we'd like to go to this location on the cliff. So this is quite delicate because if you're not quite sure how the dynamics work, you might accidentally walk off the cliff, and then you'll be in for a bad time. So if you have fairly good confidence about where you'll end up, if you try to reach that location, then maybe this is a good way to go, and you'll reach the desired goal. But if you have a highly uncertain model, and its uncertainty region is much wider, maybe you're better off being very careful and maybe not going right to the edge of the cliff, because your uncertainty from your model tells you you have a pretty high chance of falling off if you do that, right? Because for the circle, a lot of it is off the cliff on this side. So if you can get good estimates of uncertainty, maybe your model-based planner will avoid doing those things that have a non-trivial chance of resulting in bad outcomes, and you'll kind of learn more gradually. So the expected reward under high variance prediction is very low in this case, even though the mean is the same. Now, keep in mind that all these issues having to do with model uncertainty are really just another manifestation of the distributional mismatch problem. So if we never had any distributional mismatch, of course, we wouldn't have any of these issues, because then our model would only ever be tested on data from the same distribution as it was trained on. But if we have so many possible opportunities to make mistakes, the policy pi f will actually change every single time we update our model. And we might take an extremely long time to ever converge. Okay, so the intuition behind this uncertainty-aware model-based RL method would be that in step 3, we only take actions for which we think we'll get high reward in expectation under uncertain dynamics. So this essentially prevents the planner from exploiting the model. Because if we had a single deterministic model, the planner could always discover some actions for which the model makes a mistake in the direction of the positive reward. But if we have an uncertainty-aware model, if it's a truly Bayesian model that really gives us a correct estimate of its uncertainty, then we would integrate out all those cases. And in expectation, we would actually do something reasonable. And then the model will get some more data and will adapt and so on, and eventually the model will get low uncertainty in the good regions, and then we'll actually reach our goal. There are a few important caveats with this, though, to keep in mind. So when I showed this picture, I'm still talking about estimating the reward in expectation. There are a few things that there are a few reasons why you might not actually want to do this. So for example, you might still need some mechanism for exploring. If in expectation you're told going to the side of the cliff is a bad idea, you might stay away from that and never actually visit the interesting parts of the state space and never learn about the dynamics in that region. So you might still want to do something special for exploration if you have very delicate cases like this. The procedure I described is not doing any kind of pessimistic planning. So it's not saying, oh, don't do something if in the worst case you might get a bad outcome. You could do that also. You could have sort of for safety critical systems, you might want intentionally a pessimistic planner that says, don't just use the expected reward of your actions, use like the lower 10th percentile or something. That's not what we're doing here, but we could. You could also imagine doing an optimistic planner. You can say, take a sequence of actions if in the best case, if it's in the best 90th percentile, it's good. That might lead to more exploration. But again, that's not what we're doing here. So the expected value is a pretty good start. People have tried pessimistic and optimistic strategies for planning under uncertainty, and they lead to slightly different outcomes. The optimistic planners tend to explore more, but they can also get stuck constantly trying optimistic things. The pessimistic planners can be a lot safer, which is important for safety critical systems, but they might not explore enough. So it's a little bit application dependent as to whether you want to try out those things. But we'll just talk about the expected value planners for today's lecture. Okay, I haven't actually told you how to get uncertainty estimates for now, but does anybody have any questions about what I covered so far? Yes? Right, so the question is, why am I making a big deal of this now? Is this only important for model-based RL, or could it also be important for model-free methods? The answer is, we're not entirely sure. It seems to be a really big deal for model-based RL, as in it's very hard to make them work very, very well without it. For model-free RL, things kind of seem to work without worrying about this too much. But you could imagine that, for example, in the Q-learning setting, where you also have to optimize over actions, only over one step of actions, this kind of stuff might matter. That's not what's been observed empirically so far, but it wouldn't be out of the question. Any other questions? Yes?
I still have a question about the gap thing. So here you're learning only about the P as state as prime, and how do you incorporate this into your model-free part?
So the question was, how do you incorporate this into your model-free part? Sorry, which model-free part?
Like, just for a Lucius example, like how, algorithmically, how did you incorporate this?
So the question is, basically, how was this plot produced? Very simple. You just take the behavior of the model-based planner, and then you run supervised learning to get a policy. And then you run policy grading from there. So, very simple. It's not meant to be particularly clever, it's just meant to be something that allows you to initialize from the result of model-based RL. Any other questions? Yes?
Could you go forward? Sorry, could you go forward a couple slides? Yeah, this one. The next, like, for the caption of that. What does it mean expected reward is very low even though the mean is the same?
So the question is, on this slide, what does it mean when I say expected reward under high variance prediction is very low, even though the mean is the same? So when you estimate the uncertainty under your model, the mean prediction might still tell you that your most likely outcome is to get right there to the goal on the edge of the cliff. And that's a very good outcome. So you might say the most likely outcome has extremely large reward. But if you take into account the size of this uncertainty region, then you might have some rewards there that are extremely bad for when you fall off the cliff, and your expected reward value might be lower. This is to some degree a property of the problem setting. So you could imagine environments where high uncertainty doesn't necessarily lead to bad outcomes. But in many of the tasks that we care about, there's sort of like a few things that you want to accomplish, and most other things are bad. So in those settings, high uncertainty generally means bad outcomes. Yes?
When you say uncertainty estimation, do you mean estimating a set of where the states might be under this, let's say we feed?
I would say hang on to that question for a little bit, because maybe it'll be more obvious once I describe how we actually get these uncertainty estimates. Okay, let's continue.
We'll just stop for a second. It's quite interesting that he uses two examples, graphic examples, and they basically the same thing. It's falling off the cliff. One is just moving to the left, and the other one is moving to the right.
Yeah.
Yeah, that's a good solution. Like if you reduce the variance and if you have a positive monarch reward, if you're having lesser variance, probably that will. I think it's the right direction.
Yeah. I guess it's a fairly standard sort of Gaussian idea. Like you can, but no matter what your variance is, your mean could always be 0 or yeah. I'm trying to understand how. Well, they're going to explain that now anyway, so never mind. But the thing that he's trying to get at is that this uncertainty is reevaluated at each step, just like the planning before. Is that what they're doing?
I think it depends how you do it. Like in the most naive, how I would do it. You just go to the state, run the actions, and then count where you get to and see what happens. You have a distribution.
So I think this is like another component of planning. Like explore the uncertain states.
Planning rather than learning, and I'm not certain. So So this uncertainty is about the model, right? That's part of the model and not of the other functions. So it's not similar to a stochastic. Probably.
Yeah, is different. Yeah, so
Yeah.
it's uncertain about the model rather than like
Yeah.
stochastic randomness.
Yeah.
So how do we get uncertainty-aware models? Let's talk about some ideas about how we can train our neural net models and get them to actually tell us when they're uncertain about things. So one idea is to use the entropy of the output. So if you have a neural net, it takes in ST and AT, it outputs P of ST plus 1 given ST AT. That output is some kind of distribution. So maybe if your state is discrete, you have a softmax at the end, and you just have a categorical distribution. Or maybe it's continuous, and you, let's say, select a multivariate normal distribution as your output. In both cases, you can look at these distributions, and you can say, well, if they have very high entropy, then your model must be very, very uncertain. Why is this not good enough?
Doesn't tell where to explore.
So what?
Sorry, what was?
I think it doesn't tell you which way to go to decrease uncertainty.
One answer is it doesn't take reward into account. Is there a more fundamental reason why this might not be a good way to get a gauge on the uncertainty of our model?
The model might overfit and be confident, but it's wrong.
Right, so the answer was the model might overfit and it might be confident, but wrong. In fact, this is a much more fundamental issue. That's essentially the right idea, but you actually can never do this. Like, this is not a way to get uncertainty about your model. So let me explain this. Here's the picture that I had from before. And let's imagine that the blue line represents your model, and your model makes normally distributed predictions. So it takes in X, and it outputs a normal distribution over Y. Now, the optimal estimate for the variance for this normal distribution is basically the average error. And the average error for this blue line is, well, looking at the picture, it's basically 0. So this model will have an output entropy that is very, very low because its variance will be close to 0. But obviously this model is highly uncertain in many regions, as evidenced by the huge mistakes that it makes. So the variance here is low. The root of the issue is that there are two types of uncertainty, and they are very much not the same, and we can't substitute one for the other. There's something called aleatoric or statistical uncertainty, which is essentially uncertainty about the data. And then there's epistemic or model uncertainty, which is uncertainty about the model. So the picture on the right here shows a model that actually did a very good job of fitting to the data, but the data itself was very noisy. So this model incurs large error, but it's in some sense the best error it can get because the data itself inherently has noise. The data is inherently uncertain. It has high statistical uncertainty or high aleatoric uncertainty, but the model is actually a very good model. It's probably not going to get any better. So for that model in the picture on the right, we should probably trust that model even though it gets high error. The model in the picture on the left gets very low error, but the model itself is very uncertain. So the epistemic uncertainty essentially relates to the case where the model is certain about the data, but we are not certain about the model. And you're not going to get that just from looking at the output entropy, because the output entropy for the model on the left is very, very low. And the output entropy for the model on the right is actually substantially higher. So here's a second idea. Let's try to actually estimate model uncertainty. Let's try to figure out whether we are not certain about the model. When we train neural net models with maximum likelihood, we have some, P of ST plus 1 given ST AT, and we have parameters theta. So usually what we estimate is the log probability of theta given our data, which is the same if you have a uniform prior as the log probability of the data given theta. So this is maximum a posteriori estimation, or maximum likelihood estimation. What if we instead don't just try to find the argmax of this distribution, but actually try to construct the whole distribution? What if we try to estimate the whole distribution P theta given D? Now, if we can get that distribution, then the entropy of that distribution will give us an estimate of our model uncertainty. So if our estimator says all thetas are equally likely given your data, that really means you have no idea what the model is. If your estimator says this is the only theta that can possibly explain the data set, that means that you have very high confidence in your model. And anything in between suggests different levels of uncertainty. So the entropy of this will tell us the model uncertainty. And then if you can estimate P of theta given D and you want to make a prediction, then just integrate out theta. It's easier said than done, but in mathematics land, it's easy to write it down. In actual engineering land, when we have to implement these things, this is basically impossible, but let's pretend that we're mathematicians for a second. Everything is very simple. Okay, so if we follow this route and we try to instantiate this idea with neural networks, we get what's called a Bayesian neural network. So in a regular neural network, every connection has a weight. So the picture on the left is essentially what you guys implemented for homework 1 and homework 2 and hopefully homework 3. Whereas the picture on the right shows a different kind of neural network where instead of having a number associated with each connection, you actually have an entire distribution associated with each connection. So you have a distribution over weights. And that distribution over weights is your P of theta given D. Now, representing a really complicated distribution over weights is very hard. The weights can have really complicated correlations and so on. And we'd like something tractable that we can actually implement in a computer. So we're going to do what we always do in deep learning, which is we're going to use an egregious and unjustified approximation. And one of the most egregious and unjustified approximations I can think of.
This is just. So I'm not familiar with those Bayesian neural networks, but is this system, or this network, is it deterministic, the way the one on the left is?
I don't think so. Oh well, if you like in the one on the left, you could also get a distribution, right? You could softmax at the end, and it'll give you.
Yeah.
So
what you're saying, if I give it the same input
Input,
twice,
yeah.
it'll give me different answers.
Yeah.
I don't know how they work, but it's a distribution, so I guess you have to.
Yeah, well, if you can, actually no, it should give you the same input again, output again, because you would expect it to, because what it's supposed to give you is not it's supposed to give you a deterministic answer, right? It's supposed to give you a probabilistic answer, and if you, without learning, without backprop, if you use it to predict twice, it should give you the same answer, of course.
Oh, so the answer is the distribution.
The answer is just a distribution, so it's not. And I think that is something that I don't quite. I haven't used the Bayesian neural network myself, because I imagine that having all these distributions and you want to link up, you want to have a fully connected network like that with distributions instead of just simple single weight values. That must be insanely expensive to compute.
Yeah.
I would imagine that it's not.
Yeah.
Yeah, I think they even call them like naive Bayes sort of weights or something, because all you do is like you have a prior and you update it. But it's still way more expensive, I think, than a simple linear propagation, like your combinations of weights. Yeah.
The output is that distribution.
Yeah.
So that distribution is going to be determined.
Yeah. So, but yeah, I mean, maybe there's a cheap way of doing it. Did you have a comment?
Basically like you compared this with naive Bayes, right?
I think
more
yeah.
Like having prior and then do this.
Yeah, exactly.
If
yeah.
this exists, then what will be the possibility of
Yeah.
this? Okay.
Yeah. I think that's how it works. I might be totally wrong about this. I haven't used them yet.
Okay. So maybe I'll probably have a read once again and try to understand it. Bayesian and neural nets. Yeah.
Is to estimate your distribution over your parameters as a product of independent marginals. This is sometimes referred to as a mean field approximation. Calling it mean field makes it sound a lot more appealing because that's a term from statistical mechanics, and one might think that physicists actually know what they're talking about. So this can make us feel a little bit better about the fact that this is a rather simplistic approximation. All right, and then what do we choose for P of theta I given D? So theta I is the ith parameter. Well, we're going to choose a normal distribution, of course, because that's the simplest kind of distribution we can think of over continuous valued numbers. So we have a mean, mu I, for every parameter theta I, and we have a variance, sigma I. So you can intuitively think of mu I as kind of your expected value of that parameter, and sigma I as your uncertainty about that parameter. So if sigmas are huge, that means that you really don't know what the right parameters are. If sigmas are all tiny, that means that you're pretty sure that mu I is the right parameter value. There are a number of ways to train Bayesian neural networks with these kinds of mean field posteriors. I'm not going to go through it in detail in today's lecture. I'm actually going to describe a much simpler approach that tends to work very well, if not better. But if you want to learn more about these kinds of mean field approximations, I recommend checking out this paper by Blundell et al. Called Weight Uncertainty in Neural Networks, or the Arengals paper on concrete dropout. We'll learn more about the techniques behind these two papers, which are called variational inference, in a subsequent lecture. So that'll probably be covered next week. But today we're going to actually talk about a simpler way to estimate parameter distributions that does not involve any variational inference and doesn't involve these independent Gaussian posteriors. We just use bootstrap ensembles. So the idea behind bootstrap ensembles is the following, that instead of trying to estimate an uncertainty for every single parameter in your network, what you'll do instead is learn many different networks. So instead of just having one network that looks at your input ST, AT, and outputs P of ST plus 1, you have many networks. And you train these networks so they all capture different estimates of the posterior. And then the full posterior can just be reconstructed as a mixture of Dirac delta functions. So if you have n different networks, theta 1 through theta n, we'll just say that P of theta given D is just this mixture of the theta i's. So if you can train these theta i's so that that mixture is approximately equal to the posterior, then you'll be able to use this to get some uncertainty. The intuition behind this is actually very simple. You train multiple models, and if those multiple models agree on the answer, that means you have low uncertainty. If the models all disagree on the answer, then you have high uncertainty. More mathematically, if you want to integrate out your uncertainty, you just sum over the predictions from all the models and divide by the number of models. You just average your models' predictions. That seems deceptively simple, but of course you have to actually train these models, so this is a meaningful thing to do. How do you train? Well, the main idea is that you need to generate independent data sets to get independent models. So if your models are independent of each other, then this ensemble trick works and you actually get a good posterior. But if your models are obviously all identical, they'll all make the same mistakes, they'll always agree on the same wrong answer, so that's no good. So you somehow need to take your data set and you need to get n different independent data sets out of it. And it turns out that one of the ways you could do that is by taking your original data set D and resampling the data set with replacement. So if your data set has 5 items, then you generate a new data set DI by selecting uniformly distributed integers between 0 and 4 inclusive, and resampling your original data set to get 5 other data points that come from the same distribution, but they might place a different integer valued weight on the original 5 data points. So this is basically resampling with replacement.
What?
Yeah, what?
That sounds... What? Because at first I thought they were going to do a cross-validation-like thing, which is kind of what it sounds like. But why would you have different weights? What does he mean by weight on the data point? Like, is
he saying that you have like a data set?
Yeah.
And then so you have 3 different models, and so you take a third, or randomly sample a third, train one model, and then randomly sample and then train the other.
But if you sample with replacement, then you're not taking a third, and you're taking the full data set, right? So the part that I don't understand is like, why would you have? That sounds like you're just changing the order, which is just totally weird. Like that can't be the temporal order of your steps. That would make no sense, unless your data set is sampled data so that you have ST, AT, and ST plus 1, like your D, like this, because SA, S prime. So I guess but that's just independent shuffling. Wouldn't you do that anyway?
So is DI the same size as D?
That's a good question. Maybe it isn't. That's true.
Yeah, because if you add more tuples, keep on adding more data.
Yeah.
You go back to the previous.
Yeah.
The previous slide where he's doing.
Yeah. So you could get. That's right. So, right. So you wouldn't necessarily sample all of it and train again and again because you would expect 3 times the same thing. That's right. So like you said, you would have a third.
Just getting a subset.
Yeah, but you would sample. Let's say you have a set of. You could actually do it differently. You wouldn't have to make it a third. You could say you have a sample of 10, and you sample 6 out of 10 for each model with replacement, so that they don't share all of it, but share some of it by force. I wonder if there's a like a rule of thumb, as in like how much they should share. So if you have 3 models, you sample 5 out of 10 with replacement, and if you have 10 models, then you would sample 2 out of 10. I don't know whether there's a should we hold it here and go back to the bootstrapping to like start?
I'm not going to go through it in detail
today. From next time.
Yep.
And then if otherwise we could so that way we can either go to the bootstrapping, depending on how many people we have rocking up, or go to hacking if we all bring our laptops. I'll try and put the notice out a bit earlier than this morning at 8. I stepped on the train and was like, oh, I better tell people.
Is it possible to have this presentation, or is it something like
Yeah, totally. That's on YouTube. We've got the link on the on the meetup website.
Okay.
Yeah.
I'll probably go on that.
Yeah.
It's in Berkeley.
Yeah.
I'm probably reading something else. I was reading this thread, ordinance and recursive.
Yeah.
Reinforced learning stuff.
Yeah.
But this is going to a very different topic where it's more like trying to improvise the model to see that it achieves the outcomes.
Yeah.
And I think the target is to reduce the variance is what I see it.
Yeah.
If you take that example of the car, which is deviating from the middle of the road through the.
It was very interesting for us because we had read this book, Introduction to Reinforcement Learning by Sutton Bartow, and the model-based reinforcement learning didn't take up much room in that book. So it was a natural step for us to look into. And then turns out, like, I can't remember, I think I found it on Reddit. Someone posted that the current CS285 course at Berkeley. This is basically happening this month. This lecture is like maybe 3 or 4 weeks old.
Okay.
Yeah,
this is
October 7th.
Yeah, that's right. Yeah. So this is state of the art sort of university lecture stuff. So we figured that would be interesting to continue in terms of especially model-based reinforcement learning, which we hadn't covered well enough or deep enough, at least to my liking. I don't know about the rest of us.
It's also halfway through this course, so
that's true. Yeah,
it starts from.
It starts from. Yeah, that's right.
So is it like a is it more like a application based, or is this because this is going towards an application into robotics and like be it autonomous. Is that what I understand? Like
I think that just happens where they're at now.
I think this Sergey Levine who runs this course is like a roboticist, so that's like his focus.
Yeah,
but
because
I'd be slightly biased.
Because they have used reinforcement learning in autonomous vehicles and stuff, if I understand right, and they have used neural nets as well. So and they use a technique where graying and other stuff to see that the vehicle doesn't deviate and hit the dividers or.
So I guess RL is a framework for making decisions. So whatever you're doing with it is something that's going to take some actions. So
That's what you're saying.
So what does he propose? What we're going to do? What does it say? So in terms of what they've covered so far, they're doing they've got a different approach, and I think that is because, like you said, because he's a roboticist. Because I remember when I looked into Andrew Ng's courses from Stanford on RL, he said, model-based is boring. Just take a couple of this approximations, and you're done. It's fine. Yeah, and didn't look into model-based. Like it took like 2 lectures and he was done. And they're looking at it much more for maybe even exactly that reason. So it's an interesting course to look at, especially consider that when we looked at inverse reinforcement learning, it was already an addition to what we hadn't covered in the book. Yeah, and here is now part of the course So I think it's a good opportunity to catch up on what's currently being taught. Slides from the presentation. Videos themselves, there's a link. But just installing everything and getting it to run in the learning part was quite challenging to start with. Mostly because they're universities, so they get university licenses for the software packages that we can't acquire, and so we have to use freeware substitutes, which need a bit of tweaking to make them work. Yeah. Sai has started on this already last Friday.
That's why I'm a bit late, and today I was really late.
Yeah.
So are you all more into robotics, or like you're talking about electrons and stuff like?
Well, that's because I'm a physicist. But
okay.
yeah, Patrick is a roboticist.
Because that's true.
A future roboticist.
I'm a student. Yeah.
So you more at RMIT or?
Monash.
Monash, okay.
Exactly.
Yeah.
That's good. So we'll probably go to the next topic would be we'll focus on bagging, bootstrapping, and then is that what you mentioned?
Yeah, that's where he's going to, and then from there it'll go to model-based policy learning.
Okay.
Yeah.
I'll probably refresh my knowledge before. It's going to happen every Friday, is it right? Every once in a fortnight. This particular session is going to happen every.
Our session or their session?
Our session.
This is weekly.
Weekly.
We meet weekly at Wednesdays.
Okay.
Yeah. Instead of 4. Today, if you want to, it's a bit late for that, but if you want to get into a good discussion, make your way to North Melbourne, to Brain Shop, where Noon van der Silk and Laura Summers are talking about ethical AI and fairness and explainable AI today. I think the talks started I think the meeting started at 5:30 and the talks start now. So that's why Noon didn't dial in today. Yeah, so that will be, if you want to do something more about AI and network with interesting people, go to our community in, what is it, 4, I think I'm confusing it with our address, 452 Victoria Road or something. I don't remember. If you Google...
the 3 of them are probably...
Yeah, if you Google Brain Shop, or Noon van der Silk, or Laura Summers, you'll definitely
because I
find.
attended the ATO's ethical aspect in the AI. I mean, it's more about...
On Monday, last Monday.
That's right, yeah. I think so.
At Responsible AI?
Yeah,
Yeah.
Responsible AI.
Yeah, yeah.
So it's more like saying, in that the ethical concept of when you take a sample, it's possible that we might take those data points or which might be biased.
Yeah.
So is that the same talk that you're mentioning about, like ethical in the AI?
I'm sorry.
You mentioned about a talk like there's ethical AI talk going on. Is this similar to what I said? Like
no, I think Laura's going to talk about explainability in AI because there are several packages, I think in Python, for example, which are trying to kind of monitor AI training, like neural network training, for example, so that you can backtrack and see what the steps were that happened inside the neural network that led to a certain decision. And then when you can trace back where those steps came from, then you can trace back where those weights came from, hopefully, if you monitored it well enough. And then you might be able to explain how the decision came together. Or in other ways, there could be an understanding around this where the network can relate its decision to the input. So, for example, if the training had been, if it was something around, say, credit scoring, if you were given a loan or not for some reason, then you'd want to be able to say what the counterfactual is that prevented you, or that would have enabled you, to get the loan. So say, for example, your loan application is denied, and then the explainable AI part says the algorithm denied your loan because you had to have say a certain income above a certain above a certain value, and you didn't show your income being at that value for long enough. So in other words, but the AI wouldn't maybe not frame it that way. Keep your job for a year and come back, and your chances will be much better. We can't give you this. Like the things that a proper bank teller should explain to you, or should, so these sorts of things that would also be part of explainable AI.
Okay.
Yeah.
That's good.
So it's a very interesting topic at the moment. Yeah, we were actually looking at that just at the beginning with the counterfactual fairness and counterfactuals for algorithmic interpretability. So these talks, I've been looking at that over the last couple of days, trying to get back into, because we had a hacking session about fair ML on last Friday, where we tried to get into the software that they used to do this.
Is it possible to send the links that you have about this fairness part?
Sure. If you give me an email, I can invite you to our Slack channel. See you, Patrick. Thank you.
See you guys.
Thanks.
See you, Catherine.
Yeah, because I worked on this because most of the scorings they use logistic regression.
Yeah, sure.
You're most welcome. See you next time. Yeah, it's kind of clear that that's my YouTube channel, Top 20 Drum Fills of All Time.
Oh, yeah.
I like Rick Beato's channel. It's pretty cool.
That's a good lesson.
Yeah.
To go incognito to
yeah.
get rid of the history.
Yeah, well, I don't mind. There's not much. There's not much on YouTube that I watch that's bad, or not safe for work or whatever. So.
Yeah, it's I'll just type it or you can write it. It's Navin.
Navin.
Yeah.
Navin.
Yeah, Navin. KR.
KR.
Dot KUMAR.
MUNAR. Munar.
After KR, there's a dot.
Yeah.
Then KUM.
KUMAR. Kumar.
Yeah, Kumar.
Yeah.
At gmail.com.
At gmail.com.
Yeah, because I can certainly explain about the scoring, credit score, because I worked on that.
Yeah.
But this is just a logistic regression.
Mm-hmm.
Nothing more, because it goes regularly.